Welcome to Fundamentals of Artificial Intelligence. We continue our discussion on machine learning. Today we look at support vector machines. Within machine learning, support vector machine is a supervised machine learning algorithm that is used in classification and regression analysis. Support vector machines allow creation of hyperplanes within a group of inputs. Given a set of training examples which are labeled in one of two categories, a support vector machine learning algorithm is able to build a model so as when new examples come, it could be categorized into one of the two categories. A support vector machine is a non-probabilistic binary linear classifier. Support vector machines can also efficiently perform nonlinear classification by what is called the kernel trick. That is, by an mapping of the inputs to a higher dimensional space where it is linearly separable. We look at the basic formulation of a linear support vector machine in this lecture. So, binary classification can be viewed as the task of separating classes in feature space. Like what is shown on your screen here are two group of inputs, the blue dots and the red dots, and we are looking for some form of separation or a decision boundary that can be drawn between them. So, we could have a number of decision boundaries as shown here. So, we could have one, those are very close to the blues, one, those are very close to the reds, or ones that lies somewhere in between. Question is, which of the linear separators is optimal? And this is what the support vector machine algorithm tries to figure out. So, if we think of the red to be the positive examples and the blue to be the negative examples, question is, how do we divide the positive and the negative examples? And the idea in support vector machine is to have a separation using a hyperplane where the width would be as maximum as possible. So, we are thinking of a line in between these examples with a view towards putting in the widest street separating the positives from the negative examples. So, if we are thinking of putting in a line here which separates the positives and the negatives, we want that we should be able to put in as large or as wide a street as possible here. Now, we are thinking of having two parallel hyperplanes that separate the two classes, and the idea is that the distance between them is as large as possible. And here the examples that are closest to the hyperplanes, like this one here and this one here, are referred to as the support vectors, and this is where it gets its name from. The margin of the separator is the distance between the support vectors, and our idea of getting a classification margin here is to get as wide a margin as possible. So, while doing that, we want to figure out what would be the widest street that we can manage in between these positives and negative examples. And therefore, first we assume a vector which is constrained to be perpendicular to the median of the widest street possible. So, here is W, which is the vector constrained to be perpendicular to the median, and any unknown point we will refer to by a vector u. So, u is a vector that points to an unknown. Whether the unknown is on the positive side or on the negative side, how does one make that conclusion? Now, in order to look at that, what is to be done is we project the unknown vector u onto W, which is the vector constrained to be perpendicular to the median. So, we take u and let it fall on W. So, we project u on W, and then what actually that means is now we have some form of a measure of the distance of that unknown sample in the direction of W, which is perpendicular to the median of the street. So, in a sense, the larger we have that value, farther out we go, and the closer we will get to the positive samples. So, even if we do not have a clear idea of whether u refers to a positive or a negative sample, taking the projection of u on W and having some idea on what is that distance in the direction of W, we will be at least having some notion of whether it is closer to the positives or it is closer to the negatives. And if we assume a particular constant C and somehow the dot product W dot U is greater than or equal to C, then we can think of it to be nearly reaching the positives. So, without loss of generality, what we can write is we can write an equation saying instead of C now we replace with a B, and we say if I have W dot U plus B greater than equal to 0, then I am going to classify the unknown U as plus, and this could be our decision rule. So, let me repeat what our decision rule is and how do we go about getting to that. First, we think of a vector W that is a perpendicular to the median of the street that we want to fit in between the positives and the negatives, and U is a vector that is only pointing to an unknown. Now, we project U on W and we say W dot U plus some constant B, if it is greater than or equal to 0, then we are on this side, which means that the unknown U is a positive sample. However, this decision rule that we have stated, we do not have enough constraints here to fix a particular B or even a particular w. For we could have many w's perpendicular to the median line, for we have not committed to what could be the length. So, we could have lot of w's that are perpendicular to the median line, because it could be of any length. Further, we have no idea of what constant b to use, and therefore, we need to look for more constraints so as to really make our decision rule work. What is done is we say that for a positive sample, the decision function gives us value of 1 or greater. That is something we are going to insist, and we say that for negative samples, the decision function gives us value of equal to or less than -1. So, all plus sample vectors now we have, and then if all plus sample vectors refer to as x plus, then w dot x plus, which is the positive sample vector, plus b is greater than equal to 1. So, all positive samples we insist that the decision function gives a value which is 1 or greater, and for all negative samples we write as w dot x of minus plus b is less than equal to -1. So, this is the constraint that we add. So, the constraint enforces that any vector that comes to the positive side here, if it comes here, then I am going to have +1, or if it stays in the negative samples, then I am going to have less than or equal to -1. So, these are the functions on the two sides of the hyperplane that I want to fit in, or the widest street that I want in between the pluses and the minuses. So, now we introduce a variable yi. This variable is so defined that yi is assumed to be +1 for all the plus samples and -1 for all minus samples. So, for anything this side of these street, I consider yi to be +1, and on this side of the street yi is considered to be -1. Now, once we have this yi, the variable, and we multiply each equation by the variable yi, we have a very interesting thing happening here. Let us look at what that is. If you multiply this side by +1, because here we are talking of the plus samples, and for the plus samples we know yi is +1. So, we try to multiply this with +1, and once we multiply this with +1, you will realize that this very fact that I multiply this by +1, I have x w dot xi plus b greater than equal to 1, and if I multiply this by -1, I actually have the same equation. For this portion that I multiply the variable with, this becomes minus and this becomes plus. So, I will end up having the same equation, which is yi w dot xi plus b greater than equal to 1. And if I take 1 this side, this is the equation that I will end up with. So, multiplying by the variable yi which we have introduced, +1 for pluses and -1 for minuses, end up reducing the two equations that I have to 1. And now, as a special case, if I am talking of points only on the boundary, I would rather equate this to 0. So, for all points on the boundary, what I have is yi multiplied by w dot xi plus b minus 1 equal to 0. So, these are points on the boundary. Now, given the constraint that I have now got by first projecting the unknown along w, introducing the fact that anything on the positives must be greater than 1, anything on the negatives would be less than -1, and then introducing a variable yi, which is +1 for pluses and -1 for minuses, I finally arrive at this constraint equation. Now, given this constraint, what is the width that I can get on the classification margin? Now, in order to get this, we again fall back to looking at the support vectors or the samples that lie on the boundary. So, first we take a vector x1 which refers to a point which is a positive sample on the boundary, and then we look at x2, a vector that goes to a negative sample lying on the boundary, and then we can do the difference of these two vectors. So, we have w dot xi plus b, which is +1, that is the equation because of the vector x1, and w dot x2 plus b equal to -1 because of the vector x2. And now, when we look at their difference and then we project that along the unit normal to the median line, that is, you remember I had w which was the normal to the median line, and if I divide it by the magnitude of w, I would have the unit normal to the median. And now, if I take the difference and the dot product of the unit normal, so I have the difference x1 minus x2, and I take the dot product with the unit normal, what I have actually is what is this length in this direction. So, basically I have the width of the margin. So, this value here that I end up with, which is the difference of these two vectors x1 and x2 of the two samples lying at the two boundaries, when I take its projection with the unit normal to the median, I end up having the width of the margin. Now, if you look at it more closely, this difference here actually w dot x1 minus x2, if you go back and look at it here for the difference between the two vectors x1 minus x2, then what I will have is actually these b's going out, and I will have 2 here when I do x1 minus x2. So, this is interesting that the width of the margin is 2 divided by the magnitude of the normal that I had first taken to be normal to the median line. So, once I have this, and now if I want this width to be maximum, so all I need to look for is what would be the value of W, so that this becomes maximum for me. So, to maximize the width of the separation, one would need to minimize W while still honoring the constraints with regards to the values on the edges of the separation. And one possible approach to finding the minimum now is to use the method devised by Lagrange. So, the Lagrange multipliers would give us a new expression which we can maximize or minimize without thinking about the constraints anymore. So, maximizing the width is ensured if one minimizes W while honoring constraints on edge values. So, all we look for minimizing is a term half W square. So, the translation of the previous formula into this one with half and squaring is just a mathematical convenience. One needs to realize that from the previous discussion, we can maximize the width of the separation by minimizing W, and because it comes with certain constraints, we follow the method devised by Lagrange and take help of Lagrange multipliers to get to a new expression which we can maximize or minimize without thinking about the constraints anymore. So, now for the maximum margin for the hyperplane that we are thinking of putting in between the positives and the negatives, we have to minimize half W square subject to the constraint that yi W dot xi plus b minus 1 is greater than equal to 0. Now, the Lagrangian is written using Lagrangian multipliers, and we arrive at new expression without constraints. So, each of those constraints is going to have a multiplier alpha I. Basically, we write the Lagrangian L as half of W square minus, now each of these sample points I which have to satisfy the constraint is multiplied by a Lagrangian multiplier which is alpha I, and then we have this whole equation which is the Lagrangian. Now, in order to realize the extremums, we need to find where the Lagrangian has 0 derivatives, and therefore, we look at partial derivative of L with W equal to 0 and partial derivative of L with B equal to 0. So, if you derive the Lagrangian with W, so partial derivative of L with W, we have W here because of the first term, and here W is only here, the rest of them are constant. So, all we will be left with is summation alpha I yi xi. So, this is that term, and this term will vanish. So, will this final term here. And now, interestingly, what we have is what W is. So, we are now in a position to get to W being the linear sum of the samples. For, if you remember, alpha I is a Lagrangian multiplier yi is a variable that we have introduced based on whether we are doing plus or minus, and xi is the sample. So, this decision vector w is a linear sum of the samples. And when I do partial derivation of L with B, this goes away. All that I have is here B there, and therefore, I have summation of ai yi equal to 0. Now, once I have this, I can go and plug in this w here as also here, and this I have not covered in this lecture, but once you plug in there and take care of not to mess up the subscripts, we will finally arrive at the expression for L as shown on your screens. So, plugging in W into this L will finally end up giving us this equation for L here. That is what we will arrive at. So, finally, we have to find a maximum of this expression in order to get the maximum width for the boundaries. Now, this optimization is interesting to note for the very fact that the optimization only depends on the dot product of a pair of samples, and this is a very, very interesting realization. Now, let us see what the decision rule is. Recall that the decision rule was to classify unknown u's as plus if we had f of u equal to w dot u plus b greater than equal to 0. We are going to plug in the value of w that we have got into this equation. So, with w equal to the summation of the samples, now the decision rule is here. So, we see that the decision rule to classify any unknown u as plus again depends only on the dot product. So, the decision rule also depends on the dot product of the sample vector and the unknown. Now, as I was referring to in the beginning of this lecture, that support vector machines are actually binary linear classifiers, but then it can also deal with non-linear classification. Like here is a data set which is not linearly separable. That is, it is impossible to draw a line in the 2D plot which could separate the blue from the red sample. Now, the question is, under such scenario, is it possible for us to apply a support vector machine algorithm? And this is where the kernel trick plays a very important role. The general idea here is that even if the original feature space is not linearly separable, you can always map that feature space to some higher dimensional feature space where the training set then is separable. So, given this feature set which is not linearly separable, I can think of having a function phi of xi which will try to map every point in this data set to a high dimensional space. And then it would be possible to have linear separation as shown in this diagram. Now, one thing that we need to take note of at this point is that when we were talking of the linear support vector machine, the optimization as also the decision rule required only the inner product. If you remember, all it required was the inner product of the samples for the optimization, and it required the inner product of a sample and the unknown in the decision rule. That is, if we are even somehow mapping them using phi, then all I will need is phi xi dot phi xj for optimization, and I will need phi xi dot phi u for the decision rule. So, there is a requirement of only the inner product. So, all that is required is a way to compute the inner product or the dot product in the high dimensional space as a function of vectors in original space. This is very interesting, for we have something called a kernel function, that is a function that is equivalent to a inner product in some feature space. So, basically we could be given a k xi xj which should be equal to phi of xi dot phi of xj. In that case, we just need to know k, and we need not bother about the mapping function itself. So, we do not need to know what phi is given k to us, and this is what the kernel trick is. You are given the kernel, and once you are given the kernel, it means that you are given the inner product in that feature space. Once you have the inner product in the feature space, we know we do not need the explicit function that has mapped from one feature space to this feature space that we are currently dealing with. So, the kernel trick avoids the explicit mapping to get the linear learning algorithms to learn a nonlinear function or decision boundary, and this is very, very important. For now, you can think of taking something in a nonlinear space, a space which is not linearly separable, and you can get to a feature space where you could apply SVM, but then you would not need the explicit mapping. All you would need is the kernel function. Now, we have a number of kernels. I would just mention 3 here for the sake of introduction to the idea of having kernel functions and how they look or what is their behavior. So, we have something called the linear kernel. The linear kernel is the same as what we have discussed. It is just the inner product of xi and xj. Now, linear kernel is used when the data is linearly separable. That is, the data is something like the example that we saw in the lecture today. We can separate the plus and the minus using a single line. Now, the linear kernel is one of the most common kernels to be used. Linear kernels are also something that can be used when there are a large number of features in a particular data set. The second kernel is called the polynomial kernel. So, the polynomial kernel is what is shown here. It is 1 plus the inner product of the ith and the jth sample whole to the power n. Now, this polynomial kernel actually represents similarity of vectors in a feature space over polynomials of the original variables. That is, the kernel actually does not look only at the given features of input samples, but also it looks at combinations of this. One of the most popular support vector machine kernels is the Gaussian kernel, referred to as the radial basis function. So, the Gaussian kernel is an exponentially decaying function in the input feature space, and the maximum value of this is attained at the support vector, and they decay uniformly in all directions around the support vector, leading to some hyperspherical contours of the kernel function. And the Gaussian function or the radial basis function is one of the most popular kernel functions used in support vector machines. Now, let us quickly recall what is the main idea of the support vector machine that we have covered in today's lecture. We had actually looked at three very fundamental ideas today. The first of the idea is about the maximum margin classifier. So, we have formalized the notion of the best linear separator. Now, the best linear separator is the one that represents the largest separation or the margin between the two classes. That is, when we were looking at the plus and the minus samples, our interest was to get to the distance between the two classes and make that distance as large as possible. So, we were looking at the distance to the nearest data points on each side to be maximized. In a problem, if such a hyperplane exists, then it is known as the maximum margin hyperplane, and the linear classifier it defines is the maximum margin classifier. So, in a way, the support vector machine that we were trying to arrive at today is a maximum margin classifier. The second idea that is very vital and have changed the way we look at optimization is the concept of the Lagrangian multipliers, where we had a way to convert a constraint optimization problem to one that is easier to solve, bring in a new expression using the multipliers without having any constraints any longer. So, the constraints are factored into the new expression. The third of the ideas that we have explored today is the idea of kernels. Now, one needs to take note that the very idea of kernels have changed the way support vector machines have been put to use. As I have explained earlier, support vector machines are non-probabilistic binary linear classifiers. Therefore, when I have problems that are with data which are not linearly separable, application of a support vector machine is made possible only because of the kernel trick, which is about projecting data into higher dimensional space and make it linearly separable. We have looked at the linear kernel, we have mentioned what is the polynomial kernel, and also the Gaussian or the radial basis function kernel. Now, finally, to conclude, the original support vector machine algorithm was invented by Vladimir Vapnik in 1963. However, for almost 30 years, nobody had noticed this work until someone in the Bell Laboratories found Vapnik's work, and Vapnik immigrated to the US. And thereafter, he also worked on the kernel trick further. The kernel trick had a mention in his thesis, but with the use of kernel trick in big way, the support vector machines gained increasing popularity in the 1990s. The support vector machines are possibly currently the best or among the best performers for a number of classification tasks, which range from text to genomic data. In fact, for anyone who claims to have worked in machine learning or any literate in machine learning, the support vector machine needs to be in his toolbox. Support vector machines can be applied to complex data types beyond the feature vectors, such as graphs, sequences, relational data, by designing kernel functions for such data, and kernel tricks hold huge promise. Support vector machine techniques have also been extended to a number of tasks such as regression, principal component analysis, which we have not covered in this lecture. Thank you very much.